Hey there, and welcome. Today, we're going to pull back the curtain on the amazing, invisible world of chemistry that's happening all around you, literally every single second. From your kitchen to the world outside, chemical reactions are constantly shaping our lives. So let's jump right in.
It sounds like the beginning of a weird riddle, doesn't it? A rusty old nail, a steaming pile of compost, and a faded black and white photo. I mean, what could possibly connect those three things? Well, by the end of this, you'll see they're all linked by just a few key ideas in chemistry.
Okay, so first up, let's talk about a concept that's basically all about swapping partners. You can think of it like a chemical trade-off, where one element looks at another one and says, "Hey, I want what you've got." So, picture this classic experiment. You take a plain old iron nail and you dip it into this bright blue liquid. That's copper sulfate. And if you just wait a bit, something really cool starts to happen. The blue color begins to fade away, and the nail starts to get this weird brownish coating on it. What in the world is going on? Well, what you're seeing is something called a displacement reaction. You see, in the world of elements, some are just, well, they're more aggressive than others. And it turns out iron is more reactive than copper. So when that iron nail goes into the copper sulfate, it literally just shoves the copper out of the way and takes its place. And that brownish stuff coating the nail, yep, that's the copper that just got kicked out.
Now, this whole chemical swap thing can happen in two ways. What we just saw was a single displacement, just one element swapping places. But then you have double displacement, which is kind of like two couples on a dance floor deciding to swap partners all at once. Two different compounds exchange parts of themselves, and a lot of the time, this creates a totally new substance that's a solid. This solid is called a precipitate, and it just can't stay dissolved in the liquid anymore, so it literally falls out.
So elements can swap places, sure, but that's not the whole picture. Every single chemical reaction also involves energy. You got to think of it like a transaction. Energy is either being given off or it's being taken in.
Think about it for a second. You huddle around a campfire because it feels warm, right? It's actively releasing heat energy. But then you have an old film camera, which needs light to actually hit the film for an image to form. It's absorbing energy. They're like two sides of the very same chemical coin. And here's the breakdown. Exothermic reactions are the ones that release energy. An easy way to remember it is exo sounds like exit. The energy is exiting the reaction. They give off heat, making everything around them warmer. Then you have endothermic reactions, which absorb energy. Think endo sounds like into. Energy has to go into the reaction to make it work.
And trust me, exothermic reactions are all around us. Burning natural gas to cook dinner is a perfect example. Even the cells in your body are doing it right now. That's respiration, turning your food into energy. And hey, remember our compost pile from the beginning? The reason it gets warm is because all that vegetable matter breaking down is one big exothermic reaction. So what about the flip side, the reactions that need to take in energy? Well, the magic behind old-school black and white photography is a fantastic example. It's a classic endothermic process. The film is coated with a chemical, silver bromide, that absorbs light energy. That absorbed energy is what actually causes the chemical to change and create the image. It's pretty simple. No light, no photo. All right, for our last big concept, we're going to look at one of the most important chemical partnerships there is, and it all revolves around oxygen. Take a look at what happens here. If you pass hydrogen gas over heated copper oxide, they do this perfect little partner dance. The copper oxide, it loses its oxygen. We call that reduction. At the exact same moment, the hydrogen gains that very same oxygen and becomes water, and we call that oxidation. The key is, one can't happen without the other. And when you put those two processes together, reduction and oxidation, you get what we call a redox reaction. Get it? Red for reduction, ox for oxidation. It's the name for any reaction where one thing gives up oxygen and another thing grabs it at the same time. It is the ultimate chemical give and take. So, what's the big deal? Why should you care about this? Well, because once you know what to look for, you'll start to see the effects of oxidation pretty much everywhere. Remember our rusting nail from the very beginning? Rusting is just the common word for the corrosion of iron, and at its heart, it's an oxidation reaction. The iron is slowly reacting with oxygen from the air and water. Oh, and have you ever opened a bag of potato chips that's been sitting around for a while and it just smells wrong? That's called rancidity, and it's caused by the fats and oils oxidizing. So let's bring it all home and solve our mystery.
The rusting nail, the warm compost, the old photograph. How are they connected? Well, it's through two of the biggest ideas in chemistry, oxidation and energy transfer. The nail rusts because of oxidation. The compost gets hot because it's an exothermic reaction, releasing energy. And that photograph was created by an endothermic reaction, absorbing energy from light. Three totally different things, all explained by the same beautiful invisible rules.
You know, we've really only scratched the surface here. The way an apple turns brown after you slice it, the fizz you get from baking soda and vinegar, the way a cake rises in the oven, it's all chemistry. So next time you see something change in the world around you, ask yourself, is something being swapped? Is energy being released or absorbed? Is oxygen involved? You've got the basic toolkit now to start figuring it out.